Hello, welcome to the Gold Nanoparticle Colloid Solution Lab. Here's the lab question. This is a very simple lab that you can also carry out in your own school. You only need some chemicals that I'll briefly mention. The method of synthesis is called Turkevich method. And at the end of the synthesis, that's just a couple of steps, you will end up with gold nanoparticles in different sizes. The peak of the gold nanoparticle solution under UV spectrophotometer is determined to be 527 nanometer. So the question is, can you estimate the dominant size in terms of the radius, of course, dominant size of the gold nanoparticles? Okay, so here's what we're supposed to do. Before going further in the slides, I'll just put this aside. Initiating MATLAB. Okay. The first thing we need to do is to come here to what says the MNP. You have to right click on it and you have to say add to path, selected courses and subfolders. So all of the folders, subfolders should also be included. Okay, as you enter here, that should say like highlighted in a better way, unlike the other folders that are not added to your path, MATLAB path, as of now. Okay, so first thing I would like to do is to run this small MATLAB code that I gave to you. This is basically depending on the, as you can see, the polarizability values. We had already derived the μ coefficients for the spherical objects that are scattering the light, and for that we found them to be given like this, these two. All right, and all we need to do was to enter the gold, and that's the gold nanoparticle, and the outside, the surrounding medium refractive index or dielectric index, which is water in this case. So once we run this, we'll end up with this kind of a picture. And as I also discussed in the lecture slides, the extinction efficiency is getting higher as we're increasing the radius of the particle from 5 nanometers to 25 nanometers. This is expected result. There is a little bit of a very tiny redshift too that I can't really keep track of from this figure, but it is at this frequency or wavelength at this point and goes up to, let's find out together. Yeah, so that's almost the same. All right, maybe I'm wrong. Sorry about that. Yeah, it looks like it's almost the same. So there's no real redshift, but it's going, it's getting higher as we are increasing the radius. All right, so far so good, but this is not really what we are expected to do. So as you've seen, that gave us a peak at around 521 nanometers. So let's do the following. We will have to come here to the main command window, and we'll have to call the function MNP. And you will have installed this under your MATLAB folders by unzipping the file that I will be uploading to the web page. All right, so, and then this welcomes us, this new window welcomes us. It's basically, as you can see, it has a couple of windows for plotting and a couple of other parameters to be entered. So this is a spectrum we're interested in, and these are that's the diameter value. Be careful, that's its diameter. And this is the refractive index of water again, and we're interested in gold, but you can do that with silver too. I just used their own gold dash JCTXT file for the gold input file for the material constants. Okay, so like if we just run it for 10 nanometers, or in other words 5 nanometers of radius, it just gives us this kind of a result for the absorption, and the peak is at 523. If we do it at 0.5, it's still not distinguishable, as you can see from the plots. It's again at 523 nanometers. Okay, so we have to do this for a number of times till we reach the given, or the aimed value of 527 nanometers. Let's go back. Let me bring back the slides. Okay, so these are the ingredients that I was talking about. I'll come back to that later on. But if you can see here, the shifts that will come from the absorption peak shifts will come from the size differences of the gold nanoparticles that are synthesized at the end of the reactions. All right, so if you look at the table that's given here, it starts with 5 nanometer, it goes up to 50 nanometer. I did it for you, the results are here. And I kept track of the resonance peak, which is also designated here as well. Luckily, keeps also track of the peak for me. So I'm interested in 527. So it's between 20 and 22.5 nanometers in terms of the particle size, the radius. So that makes 40 nanometers of the diameter and a 45 nanometers. So let's try to find out which one is the correct value, or correct, let's say, 40 and 45. So let's start with 42.5 nanometers. Yeah, that just jumped. We just found it immediately at 527 nanometers. That's the middle point. I guess similar values would also be attained by, let's say, 42 nanometers too. Yeah, so we have a kind of a range that we can really determine just solidly based on this, the precision of this, basically. And the crude precision is mainly due to their crude gold material data, unfortunately. If you look at it, there are only a few points that are available in our specific interested region. So it's not the best data that you would like to play with, but still giving us a first-hand approximation. So my range is like from 41. Yeah, 41 still gives me 527, and can go up to 43 maybe. Yeah, that still gives me, so somewhere around 41 nanometer, 43 nanometer. My particles are in this range. Go back. So this is a picture that I got from a slide. Sorry, I got from a paper that's highlighted here. So that's the final color, of course, that we're going to attain, because as you can see, most of the other wavelengths are absorbed in this whole optical interaction by the colloids. And then only the red spectrum that is remaining for us, that's the least absorbed portion of the spectrum. And that also is determined by the particle size. So once you synthesize these gold nanoparticles, they come in different sizes. There is not just one specific size that you can attain immediately. People are working on different synthesis methods, but if you go back to the synthesis method, basically, you first need to get this kit, which makes your life much easier. But people mainly start with a gold to synthesize gold nanoparticles, of course, gold salt solution. So that's the procedure. The gold salt solution that I was referring to is this hydrogen tetrachloride. So you mix it with DI water. Once you mix it with DI water, the gold salt, okay, HAuCl4, gets ionized, and the gold ions, they are in the form of +3, so they reside inside the water. By the way, I don't think it may not have to be DI water. You can do it with not just deionized water, but normal water too. I'm not 100% sure about that. But once you add the gold salt solution, the gold will ionize for sure, and they will get +3 charge. At that point, you need to add what's called the reducing agent or the capping agent around these kind of gold nanoparticles. So those kind of agents will cap the surface of the gold nanoparticle, okay? And they will reduce the total charge of the gold nanoparticles as well. In this case, what we are using is sodium citrate, okay? A little bit amount of sodium citrate, and this is really not very harmful at all. Once you add that to the solution, that caps the surface of the gold nanoparticles, and thereby the total net charge of the gold nanoparticles get stabilized. So we also use these kind of capping agents as stabilizers too. In this way, they do not aggregate. Originally, let's look at a scanning electron microscope image that I got from our SEM here at Penn State for you. Once you do the synthesis, of course, they never as soon as you introduce the gold salt, they're still not like this, not forming clusters like this. They're just sitting inside as ions, gold ions, ionized gold. To start the nucleation and also to stabilize the nucleation as well, you need to add the reducing agent like we talked, that's the sodium citrate, and then it caps itself onto these kind of nucleation sites and gives you all these kind of different diameters, as you can see here, 32 nanometers, 25, 15 nanometers. They're all changing in sizes, and that will make it a negatively charged particle with the capping agent on the top, because the sodium citrate, as I told you, is negatively capping the gold nanoparticle. And then these will be, due to the Coulomb attraction and also repulsive forces, negative charge particles would not stop nucleating with each other at that point, and works as a stabilizer for that reason. So we end up with these kind of diameters. But as soon as you introduce another agent, that's the screening agent, into the water, your solution, after you synthesize the gold nanoparticles, of course, the the screening agent would neutralize the negative charged effects of these kind of capping agents, the sodium citrate. So we mostly use table salt, basically sodium chloride, for that purpose, dissolved in water. Once you add that into your solution, the gold nanoparticle solution, the sodium chloride, the sodium ions would basically go and fetch these kind of capping agents and neutralize their negatively charged effect. and thereby you would lose your nice dispersed nucleation size inside your solution, and then they would start to aggregate one more time, and you would lose the localized surface plasmon resonance action, and the solution would of course turn back to a transparent, I wouldn't say color, but it would become transparent rather than the red color. Originally, after the synthesis, of course, you would see them in a red color. So that red color of the solution that's shown here will turn to a transparent color because of the aggregation of these kind of nanoparticles. Okay, so that was it about this lab. I hope you enjoyed it. So see you in another one.